All right, good afternoon, everyone. Today we are going to finish essentially all of the lecture components for this course. After today, we will just do review sessions. So we'll meet on Friday and do a review of the practice exam 4. And then we'll come in next Monday and do the exam that covers all of unit 3. Just a reminder, all of your homeworks and all of your quizzes, so quiz 6, 7, and 8, will be due on Monday at noon. So the more you get done now, the less you have to do later when it's really crunch time to study. So that'll be coming up. I will open up quiz 8 and homework 3.7 today, but hopefully you've looked at quiz 6 and 7 and at least started the homework for units 3.1 all the way to 3.6. Okay. So yeah, let's get into solutions. My goal would be to finish solutions today. If we don't finish today, that's okay, but it is going to be a math section, so please get your calculators out and ready. Any questions before we get started? So reminder, our exam will be this upcoming Monday, starting at noon. We'll have everyone come in and get settled, and then once everyone's settled, we'll start the exam immediately. So you'll have the whole class period like we did last time. Before we get started in solutions, let's just do a little bit of review. We've done a lot of extensive discussions over ionic versus covalent compounds. So if I was to say ionic or covalent, can anyone like tell me what that makes you think of? Like what makes up an ionic bond or a covalent bond?
Ionic is metal and non-metal.
So to make an ionic compound, it is a metal plus a non-metal. Anything else? So covalent is only made up of nonmetals. There are some more words. We did have like a couple slides on electrolytes and non-electrolytes. So if I was to say electrolyte, would that be ionic or covalent? Why?
There's some kind of metal in there.
You're right. So ionic compounds will break up into ions. So electrolytes also break up into ions. So since electrolytes are ionic, that means non-electrolytes have to be covalent. You can put breaks up into ions. So and then we haven't really hit this yet, or I don't think we will. Maybe in a future 1320 class we will, but acids, bases are also ionic. So they may have the covalent, meaning that they might be all nonmetals, but they do have ionic tendencies, so those will go under ionic. But yeah, there's a lot of different things we can kind of contribute to ionic and covalent from everything we've discussed over this course. Mostly ionic compounds are metals plus nonmetals, and covalent compounds are all nonmetals. So you also need to be able to remember naming. So if it's ionic compound, kind of don't use those prefixes like we discussed for the covalent. If it was like sodium chloride, you just say sodium chloride. You just add an IDE on the end of the second word, and that's it. If it's a metal in the transition, you would also need to include the Roman numerals to be charged. So let's say manganese has a 2+ charge, it'll be manganese in Roman numerals 2, and then whatever else next to it, whether it be sulfate or a F2. All right. Covalent compounds, those do require those prefixes, with the exception of the mono on the first one. So if I was to have like NO2, it would be nitrogen dioxide. So you still have the IDE on the end, but that prefix tells you how to do that. So that's just a review. We're not always going to be so nice and spell things out for you. So if I was to say something written out, could you go from that into what its identity is? So you're gonna see that a lot in this section. Let's keep brainstorming. Let's sketch the arrangement of particles in a solid, liquid, or gas. So does anyone remember what a solid would look like if I'm just focusing on the atoms?
they're all super close.
Yes, so solids do not fill the volume of its container. So let's say I have a box here and I have just a solid in there, like it would be a bunch of particles just kind of stuck together and they would, create a shape. So if it was something else, maybe it would fill the space that's in there, but solids don't. They just stick together as a clump, regardless of what shape it makes. So I'll do it S for solid. If I did a box for liquids, what does a liquid look like? Particle wise.
Or spread apart, they fill up the whole, whatever contains there.
They do fill up the volume with the exception of where the liquid line ends. So like, let's say if the liquid is right here, it will fill the container with the liquid, but it won't fill the entire box. So yes, it does fill the volume. So I would do, particles, more spread out. They are very close to each other because that's how the liquid is made, but it fills that volume. But it's not going to be as tight as a solid would be. The solid will be the tightest held together, the tightest. All right. Last box, we'll do a G for gas. What do those particles look like?
All square.
So they're not going to be as close together as liquids and gases. I'm sorry, liquids and solids. And they fill the entire volume. So they spread out and they fill the entire container. So if you compare the distance between atoms, solids will have the least amount of distance between them, followed by liquid, followed by gas. And then gas will spread out to fill the entire container. Okay. Does that make sense? If I was to ask you to draw that, would you be able to? Okay. Doesn't have to be pretty. Obviously, I'm a talented artist. So I don't expect you to be as good as me. But if you draw something like this, I would easily be able to understand where you're going. We're going to do solutions. This whole section is solutions, which tend to be liquids. It is possible to have a solution that's a solid or a gas, but I think in general chemistry, we just focus on liquids because they're the easiest solutions to make. All right. Sketch the arrangement of particles when sugar and salt dissolve in water. For simplicity, use different circles to each type of particle and create a key of the chemical formulas for each type of circle. Omit the water molecule. That's important because water would definitely interact with everything, but if I was to leave water in there, it'd be a giant mess. So we're only focusing on sugar and then only focusing on salt. Let's look at sugar. This is sucrose. Is it ionic or covalent? So this is where I see students make a lot of mistakes. They forget that covalent molecules do not break up into ions. And they'll try to take this compound and say, okay, now I have C pluses and H pluses and O minuses in here. It does not break up into ions. Yes, I can get sugar to dissolve in water. What that means is I can take a large amount of sucrose and it'll break up into individual molecules. So they're just not attached to each other like a solid anymore. But they are floating around in solution as the entire molecule. So if I was to just do sucrose, let me do a line to represent the liquid line. And you can just say sucrose will be these circles. So if it was a solid, it would look like this as a clump of, let's say, sugar, especially if your sugar is around water, it'll absorb the moisture in the air, it clumps together. But the second it hits solution, that tight sucrose solid will break up into individual molecules. The molecule's just the C11H12, or sorry, C12H22O11. Salt's a little different because salt is an ionic compound. So when it hits a liquid like water, it breaks up into all of its individual ions. So for salt, I would have to say Na plus and Cl minus. So I'll just do different circles to represent the different charges. But just know if you see a blue circle, it's a sodium, and if it's a green circle, it's a chloride. So salt, when it is as a solid, it is still looking like that solid particle. It's all clumped together like that, but the second it hits water, and this is how it works. I can get up that really good simulation that I showed you a long time ago. So because it has those charges, water also has some polarity to it. Those oxygen are electronegative. So what they do is the oxygen will surround the sodium and rip it off from the solid. The positive hydrogens will rip off the negative chlorine, and that's why it dissolves in water. It helps bring it apart and rip it apart. So in this solution, it is dissolving in water, but it just goes one step further and goes into ion. I want to point out, is this a macroscopic representation, a microscopic representation, or a symbolic representation? The picture I drew. So symbolic would be these letters here, like if I was to draw it, so you're on it. I do have letters. But the way I would kind of draw this symbolically would be if I had NaCl as a solid, and if it breaks up into ions, it'll be Na plus aqueous plus Cl minus aqueous. So that would be the symbolic representation of what I have on the right. So very, very close. What do you think? It's not symbolic. Microscopic. So if I'm drawing atoms and if I'm drawing molecules, that would have to be microscopic because the only way you can see it is under a microscope. If I was to draw this as a macroscopic, you wouldn't see anything. You would see maybe a white clump go into water and now your water's clear. If I take sugar, dissolve it in water, it's still clear. If I take salt and dissolve it in water, it's still clear. So a macroscopic would be, what do you see if I do it like in front of your eyes? So because particles are here, this would be a microscopic drawing. I do like to add, you will see this when you take my lab, is I will sometimes ask questions where I'm like, draw this microscopically, draw this macroscopically. And then symbolic would be, of course, the balanced reaction. So going back to balanced reaction, I'm starting as a solid because I haven't added it into anything. But if I add it into water, it breaks up into its ions, and that AQ tells you it's dissolved in water. So solid is solid. Of course, AQ is also a liquid. So it's kind of synonymous, but the AQ tells you what are you dissolving it into. I want to real quick do the symbolic version of sucrose. If I was to ask you to do the symbolic version of sucrose here, you would start with C11, I keep messing up, sorry. C12, H22, O11. And if I start as a solid, what happens? So students will try to force it to break apart, but it doesn't. So you just keep it together. But instead of having it as a solid, you would change it to aqueous because it does dissolve in water. It just stays as its whole molecule. So that would be the symbolic representation of sucrose dissolving in water. Maybe you'd see a question like this on the exam. Hopefully it wouldn't be too hard of a question, but focus and say, okay, if it's covalent, it stays together. If it's ionic, it will break into ions. So that's when you have to remember metal plus non-metal, and you might have to remember your polyatomic ions because they also break apart. Any questions on that?
We would have to write this out. You also have to add the plus H2O on both sides.
No, that's a great question. If I didn't have that aqueous in there, then sure, you could add the H2O, but the H2O is not affecting anything. It's not changing the balanced reaction. So instead of us adding it in to make it part of the reaction, we just add it in like this. This is me telling you that you're dissolving it in water. So you don't have to add the H2O if you have aqueous.
When it's aqueous, is it only when it's dissolved in water?
Yes.
That's the only way it can be aqueous?
Yeah. If it was dissolved in something like hexane, we wouldn't do aqueous.
Oh.
Mhm. Any other questions on that? I almost kind of jumped the gun here. I do want y'all to get very comfortable knowing the difference between all of these definitions. So a solute is a substance that dissolves. So if I take sugar and I dissolve it in water, my solute is sugar. That is, what you're focusing on. The medium that you use to dissolve a solute is a solvent. So water tends to be a very popular solvent because it's the cheapest. We use it a lot in our labs because of that cheapness factor. We already have the sinks in there. So that's why you'll use water the most. Believe me, we like to save money. Sure labs. But you can do other types of solvents too. If you get further on in chemistry, you might see hexane or ammonia or all these other different types of solvents. But water is the most popular. A solution is the combination of everything. So if I was to dissolve sugar in water, it's sugar plus water equals your solution. So solute, the substance that dissolves; solvent, the substance that dissolves the solute; medium, solution is the combined everything involved. And then aqueous describes a solution where the solvent is water. We've already seen that a lot in this class, but get comfortable knowing AQ tells you your solvent is water. So it's really important to know the difference, and let's, practice. Some beverages, such as Kool-Aid and Gatorade, can be made by taking a pitcher of water and adding a powder and stirring. What are the solute, solvent, and solution in this case? So let's focus on Kool-Aid. Let's say if I dissolve Kool-Aid in water, what is the solvent? The Kool-Aid powder. What is the solvent? Water. And what is the solution? Sorry, say that again. All of the above. So it's Kool-Aid and water. So you have to incorporate both for this to be correct. So if I was to ask this as a multiple choice question, don't be tricked by it. Solution's just everything. But you have to incorporate solute and solvent. One moment. My phone's blowing up. Okay. All right. So we are now going to move into some definitions. Concentration is a very popular term, you'll see, and it can represent a lot of different things. So we tend to kind of think concentration is just one thing, but it's not. It just tells you the amount of solute present in a solution. It tells you the amount of something. If I was to go one step further and define it, then sure, there's a different definition. But concentration is just a blanket term for an amount of something. So you might have heard terms like concentrated or dilute. That also tells you how the concentration is. So it's the amount of a solute present in a sample of solution. There are many different units used because different units naturally follow different applications. So like if I wanted to focus on maybe a gas and I'm dissolving in a gas, I would use different units than a liquid, a solid dissolving in a liquid. So very, very different. And that's why it's very important for us to understand what is a solute, what is a solvent, and what is a solution. There are three common units: molarity, percent by mass, and percent by volume. In the rest of this section, we are going to do molarity only. But when you hit Gen Chem and maybe even further, you will see these other definitions. So when you hit those other definitions, make sure you really, really understand what is a solute, what is a solvent, and what is a solution. The definition of molarity is moles of solute divided by liters of solution. So we use capital M to represent molarity. And what I will tend to do is when I see a capital M, I will always break it up into a definition so I can understand things a little bit better. Because capital M, sometimes I can't really see what's going on. So I want you to get very comfortable recognizing capital M is moles of solute, and then the bottom number is liters of solution. Or Dr. Patterson recommends you can do moles divided by volume. Let's use some examples. Find the molarity of the solution created by dissolving 10 grams of glucose in enough water to make 250 milliliters of solution. Sketch the particle diagram for the solution omitting water. There's two things in this problem, so don't forget to do the second part if I was to turn this into a short answer question. But we kind of also need to remember kind of everything we've learned this semester up until now. This is why I love chemistry, because I feel like if you know something that we discussed, a while ago, we can build on that and continue answering these questions. We know, okay, let's also kind of think about first. So V is the variables. They're telling us I have 10 grams of glucose. And I know I have a volume of 250 milliliters. So those are the variables they give me. And I know if it's asking for molarity, capital M is mole. And we can identify what is the solute here. So is it glucose or is it water? Glucose. And the bottom is going to be liters of solution, which is the combination of water and glucose. So I'm just going to do SOLN for solution. I need to go from grams to something to moles per liter. There's something missing in between because I can't just go from grams to moles per liter. Does anyone know what I might have to do first if I have grams of glucose?
Find the molar mass.
Yes, you have to find the molar mass because if I need to go and use moles at some point, I can't leave anything in grams. But if I need to find moles of something, I would need to have the molecular weight or molar mass of our solute before I could even get started. So this is when you need to go and figure that out by, taking 6 carbons plus 12 hydrogens plus 6 oxygens. If this was a homework problem, I also recommend just Google and molecular weight of glucose and it'll pop up. But for an exam, you might have to figure that out. So go ahead and calculate that for me. Carbon is 12.01 grams per mole. Hydrogen is 1.008 or 1.01, and oxygen is 16. While you do that, I'm going to erase everything so I can give myself some space. All right. I got, I think 180, wait, might be wrong. 180 point something, 156, did y'all get that or something around there? So molecular weight equals 180.156 grams per mole. And it's okay if your last decimal places are a little bit off from me. You'll get the right answer in the end anyway, if this was a multiple choice or even a short answer. Yeah. Step one with this problem is if I know I need to have moles of something, I need to go from grams to moles. So that's just dimensional analysis. We've already done that before. So you'd start setting up what you're given, my 10 grams of C6H12O6. You can also write this out as glucose. And I want to cancel out those grams and be left with moles. Okay, so what I have to do here is to have moles on top. So that means I have to take the inverse or put the 180 on the bottom. That way my grams will cancel and I will be left with moles. So type this in your calculator, just take 10. You can either multiply it by 1 and then divide it by 180, or you can just do 10 divided by 180.156. So I got 0.0555 moles of the solute, C6H12O6. All right, it's asking for molarity, moles per liter. So I can't stop the problem here because I've only found half of it. So the next thing I have to do is calculate the molarity with liters of solution. If I'm dissolving this many grams, the liters will have to be, the number they give us, so 250 milliliters. But are these units the same? So milliliters is not the same in liters, and these problems will tend to give you it in milliliters, so we have to remember to do conversions. So does anyone have that conversion factor for me? Not once, because there are 1,000, yeah. So there are 1,000 milliliters in 1 liter. So if you're gonna do the decimal, just make sure you move it, 3 times. So if I have 250 milliliters, I can move that decimal place 3 times, like that. Or I can do the conversion factor, 1 liter divided by 1,000 milliliters, and that's 0.250 liters. All right, here's where you just got to put it together. And I'm going to focus right here. Look at this equation. I have my top number, I have my moles, and now I have my liters. So you need to just divide your moles by liters to get the molarity. So I'm going to erase this real quick and show you. So I'm going to come over here, 0.0555 moles of C6H12O6 divided by 0.250 liters. And I got 0.222. Check my math because I might make a mistake. Yeah, I got 3 twos. Perfect. All right. If you are someone who would rather do this all in one step, I can also show you how to do that. But just remember, do what's best for you to get the best outcome. And so if you feel like you can't see what I'm about to show you and you'd rather break it up into multiple steps, that is fine. There is no one way to do this. If you want, like I said, to do it all in one step, it would look something like this. Move this over.
So what's the unit or final answer?
Capital M will be the unit. You can also do moles per liter, but if you're gonna like summarize the end, molarity is capital M. All right. So if you wanted to do it all in one, and you can see it very well, and you just feel very comfortable with this math, this is just a giant dimensional analysis setup, and it's all about the units. So if you ever try to do this, keep those units in there. Don't just plug numbers in. Don't do that because you'll never be able to, I won't say never. It'll be very hard to check and make sure that you have things in the right position. Our goal is to have units moles over liters. So if I look at the way that I set this up, my grams will cancel and I will have moles on top. I cannot multiply it by the liters here because my liters need to be in the denominator. So all I did was flip it or just put it 1 over the liters. So my liters are on the bottom. So my units make sense. So that's one way you can do it. You can do it all out in one just to make sure your units are consistent. But I tend to kind of break it up and I will get the numerator and then I'll get the denominator and then I will divide them out. So those are two different methods for solving this problem. You just need to do what's best for you. Okay. Don't forget the last step. It does say sketch the particle diagram for the solution, omitting water. Is glucose a covalent molecule or an ionic molecule? So if I was to add it to water, would it break up into ions? No. It might start off as a clump. I'll keep it in red. So if it's a solid, it's a clump of glucose. But the second I add it to water, those glucose molecules will separate and dissolve in the water. So they'll just float around in the water. They'll be nice and dissolved, but they don't break up into ions. Any questions on that? We will get more practice. I promise this isn't the only thing you're going to see. All right. Here, I'm going to have you do a little bit of 2A on your own because we have, done another question very similar to this. But this is where I have to remind you to remember everything we've discussed so far. Because when I read this question, find the molarity of the solution created by dissolving 10 grams of magnesium chloride. What is magnesium chloride? So look at the periodic table of elements. So magnesium is in column 2. It's a metal. And then chloride, column 17, it's a nonmetal. So if I was to put magnesium chloride together, is this correct? Why? Yeah, because that magnesium has a 2 plus and chlorine has that minus, this would mean you'd have to crisscross them to have equal neutral charge. So the correct version of magnesium chloride would be MgCl2. So if you were to find the molecular weight of MgCl, it would already start you off in the wrong direction. So just remember to kind of break it down if you have to, get the nice version of it, or sorry, the correct version of it. And this problem is almost the exact same as the previous problem. So you need to go from grams of magnesium chloride to moles using molecular weight and then find molarity. So I'll let you do that. Start by finding the molecular weight of magnesium chloride. And then I'll write down, capital M is moles of MgCl2 over liters of solution. So I'll give you a few minutes to try to solve for this one, and then we'll do it together. So similar to the last problem, we have to start by converting grams to moles using the molecular weight. So 10 grams of MgCl2 times moles of MgCl2 divided by the molecular weight. And I got 0.105 of MgCl2. To find molarity, the next step is to take your moles of solute divided by liters of solution. So it's saying I have 500 milliliters of solution. I can't just divide this by 500. Milliliters and liters are not the same unit. I have to divide by liters. So 500 divided by 1,000 is 0.5 liters of solution. Option two, I just showed you two different ways you can do this. Option one would be breaking it apart, finding the top number divided by the bottom number. Option two is kind of putting it all together. And so you can see how the math also makes sense. So, your grams will cancel and you'll be left with moles. And then I still have liters in the denominator here. And then same thing here, grams and moles divided by liters. So the big step here would be don't divide it by milliliters, divide it by liters. Did you also get 0.210 when you tried it? Perfect. The last part says, sketch the particle diagram for the solution. Magnesium chloride, is it covalent or ionic? It is ionic. So if I was to take magnesium, let's do chloride. They're ions. So yes, they can create a solid, but the second they go into water, they will break up into their individual ion component. So if I was to ask you to draw a particle diagram of an ionic compound, you must show me it breaks up into those ions. You could also put in the dots, you can put like, I have magnesium 2 plus and then chlorine minus. Like you can also put those inside the dot to let me know. I'm just very lazy, and that's okay. Let's keep thinking about this. MgCl2. Using your answer to molarity in example 2a, what are the concentrations of this solution? We just did this one. First, let's conceptualize this and then I'll show you the math. This is when we kind of think about dimensional analysis. So if I have magnesium chloride, we just did the math here. It is the same number as the previous slide, 0.2210 molar, so capital M, of magnesium chloride. All right, now let's focus on just the magnesium. So MgCl2 will break up into Mg2+. So if I have 1 mole of magnesium, or 1 magnesium chloride, how many magnesium are in it? 1. Sorry, I know I'm kind of saying it like it's a trick question, but it's not. Essentially, what is the subscript that follows it? If it's nothing, we assume it's a 1. So in this case, whatever my concentration of magnesium chloride is, it should be the same concentration of magnesium because it's a 1-to-1 ratio. If I have 1 magnesium chloride, I will have 1 magnesium. Now, if you have the math, you would just take the, let me show you the math down here. If I have 0.210 molar, I can also break that down into moles per liter. And I use stoichiometry. So it's dimensional analysis, what we did during unit 1, or stoichiometry. I have a 1-to-1 ratio. So 1 mole of Mg2 plus for every 1 mole of MgCl2. That's exactly what we just said. If I have 1 mole of magnesium chloride, I will have 1 mole of magnesium. So my moles of magnesium chloride will cancel, and I will be left with 0.210 molar So you can conceptualize this. You don't have to do the math if you're very comfortable with the conceptual, the theory. But if you're like myself, the math will always give you the right answer and it can always be trusted. So if I have magnesium ions, just magnesium ions, it would be the same number as the magnesium chloride. So 0.210 molar of magnesium. All right. If I have 1 mole of magnesium chloride, how many moles of just chloride ions? So how many chloride ions are in every mole of MgCl2? 2. So conceptually, I should have twice as many chlorides as I do magnesium based on that theory. So what should I do to this number to get the total amount of chloride concentration? Double it, multiply by 2. The math will back you up anyway, but if I have twice as many chloride as magnesium based on, this setup, it should be 0.420. And I don't have to do a big equation if I'm comfortable with that. But I will always do it just to double check. So based on that theory, if I go back and redraw this picture the correct way, I should have twice as many chlorines as I do magnesiums in this particle diagram. So I drew 4 blue circles to represent magnesium, and I drew 8 chlorine green circles to represent the chlorine. So let me just correct my particle drawing. So I'm going to have 4 magnesium, and I should have 8. Doesn't matter where I put them. So that would be a corrected version of magnesium chloride dissolving in water. Any questions on that? So this kind of a question, I can ask you a million different ways, and I could ask you like, okay, I have 1 mole of sodium chloride. How many moles of sodium ions? How many moles of chlorine ions? Like it's the same concept. If I said I have, calcium chloride, CaF2, it's the same setup. All you have to do is be able to break it up and kind of identify, here is my ion, or here is my ionic compound. Let's just break it up into its ions and use those subscripts to kind of do that ratio. So this question can be asked a variety of different ways. Let's keep going. This one kind of really tests our conversions. And I do recommend if you have to do a bunch of conversions, just break it up because it's hard to do all of the conversions at once. But if you are comfortable doing them all at once, I will never tell you not to. Okay. Find the concentration and molarity of the solution made by dissolving 1 teaspoon of table sugar in 8 fluid ounces of coffee. So we're still doing molarity. So the first thing I need to do is figure out moles of table sugar, and I also need to figure out liters of solution. But they give us weird conversions. They say teaspoon, which I've never seen before in this class at least, but they were nice enough to tell us a teaspoon of sugar weighs 4 grams. So instead of me putting 1 teaspoon here, I can say 4 grams of table sugar. And then I can convert that to moles of table sugar. And then they were nice enough to say, okay, I have 8 fluid ounces of coffee. So I can convert that using this conversion from fluid ounces to milliliters, and then milliliters to liters. And then once you have those two numbers, you can divide them. Okay, so let's do that. First, find the molecular weight of sucrose or table sugar. I'll give you a moment to do that. And then if you wanted to get a head start and solve the rest of it, you can. And then we'll come together after the break and do the answer together. We have a 5-minute break right now, so let's come back at 12:55 and then we'll do the answer together.
Recording in progress.
Okay, let's answer this. Let's start by going from grams of sucrose to moles using the molecular weight, which I got 342.296. I got 0.0117 moles of glucose. Next, let's figure out how many liters. If I have 8 fluid, and I'm just using like abbreviations because I'm lazy and do not want to write it out, you're welcome to. Using this conversion, I can put 500 milliliters on top and 16.9 fluid ounces on the bottom. That way those units will cancel and I'm left with milliliters. But I can't have milliliters here, I have to have liters. So I have to then convert it to liters. And I got 0.237 liters. Let me check my math, check my math and let me know. The last step is to combine them. So I'm gonna kind of just, instead of me rewriting it, I'm gonna put a little line here to say, this is the numerator, this is the denominator, just divide 0.0117 by 0.235, and that will give you the answer in molarity. So that math got me 0.0494. Capital M for molarity, C12H22O11. And then check my math and make sure it's correct. This is just a fun way of combining things. We did unit conversions a while ago, but this is the same concept, even though it's a new concept. It's something that we can still answer. Using our ability to convert units, we can answer any problem, even if it is a little new to us. So that would be the first step, is convert things to moles, convert things to liters, and then you can combine them.
What's the difference between this sugar and then the glucose from example one?
They're both sweet. So
Another,
table sugar is sucrose. But glucose is like
oh,
what your body needs, like, you know, that for sugars, yeah. But it's all sugar, types of sugars that your body kind of needs.
that kind of use the numbers from the first example.
Oh, yes.
Okay.
So this one had slightly different ones. Okay, let's move on. So I kind of hinted at this before, concentrated versus dilute. So concentration tells you an amount of a substance. Concentrated means there's a lot more substance dissolved in a volume, and then diluted means a lot less substance. So if I'm looking at this picture in the top right, this is Allura Red. It's a chemical food dye that's used in a lot of stuff like candy, or sports drinks. So like our sports drinks wouldn't be as, I guess, okay, I'll kind of get into my spiel because I do this with my students a lot. America, for some reason, thinks that having a lot of dyes in our food makes us think, oh, more nutrition. So that's not true. We put a lot of dye, and some dyes are FDA approved. Allura Red is FDA approved, but they have been some papers reported that Allura Red and hyperactivity in kids, not Allura Red, but food dyes and hyperactivity in kids is a trend. So a lot of people are trying to like take out dyes from our foods. And I do hope that we kind of go more in the European route. So like European Fruit Loops are nowhere near as bright as our Fruit Loops. And that's an example of how like Americans like food dyes. Did you know that oranges are not that orange? We add dyes to our oranges to make them more orange. So in our heads, we're like, oh, more orange, more nutrition. No, because I know, for instance, my family has an orange tree out front and it's not as bright. It's like more of a yellow orange than it is a bright orange. So that's just my spiel on food dyes, but we can do it a lot in chemistry. But if you can, I'd recommend not consuming food dyes. But it is FDA approved, so it's not going to kill you. But if you have kids, I don't recommend giving them food dyes. All right, so let's talk about concentrated versus not concentrated. So concentrated means more of a substance. So if I have Allura Red food dye and these two things, which one do you think is more concentrated? The one that's more red, right? So the darker the color means there's more dye in there. So I guess I can do left and right. The more concentrated, the more dye, the darker. Which one has the higher molarity? Yes, the one on the left, because higher molarity means more of a dye in there. Which one is dilute? The right, because there's less. So the less red, the more dilute. Which one has the smaller molarity? All right. So sketch the particle diagrams in the beakers omitting water. So let's do that. What difference do you think we should see if I draw this particle diagram? There'll be a lot more in the left one. So if I do like red circles, I should have a lot more of those red circles on the left side because it's more concentrated. There's more of it in solution. I like these types of questions because they're not as hard as I think it seems. If I was to ask you something on the exam, I'm not trying to trick you, and you could always clarify with me. But I could give you some pictures like this and ask you like which one's more concentrated, which one's less. I can have you draw it. But as long as you can kind of recognize concentrated means more solute, more substance, it should be the left versus the right, and the color could tell you a lot. Yep. Let's go, we're just gonna keep using molarity here, but it says rearrange to solve for moles of solution, solute. So if I want to rearrange and isolate moles here, what should I do? If I multiply by V on both sides, that's volume in liters. I now get moles equals my molarity times my volume. And if I was to continue using the units, that would be moles per liter times liters. So you can see it cancels out to give you moles. That's why you always want to include your units, because instead of memorizing this equation, your units will help you figure it out, but both will give you the right answer. Let's practice. How many moles of sodium sulfate are in 35 milliliters of 0.25 molar aqueous sodium sulfate solution? So before I can really do anything, I like to make it a habit of knowing what is sodium sulfate. Sodium is a metal, column 1. So what charge should I give it? Okay. What is sulfate? Y'all remember? Close. And then the charge? Minus what? Yes, 2. Okay, so this one would require a crisscross. So this would be Na2SO4. You might not need molecular weight. So if I was to give you grams or ask you to solve for grams, that's when you need the molecular weight. So in this problem, I don't see grams at all. So I don't want you getting tripped up and thinking, okay, let me find the molecular weight, throw that in there somewhere and confuse myself even more, because I don't need it. But I still want to make a habit of knowing what it's asking about. So Na2SO4. It's asking for moles. In the previous problem, so capital M equals moles per volume. I rearranged this to get moles equals molarity times volume. So we can continue that same concept here. If I have 0.25, and I always will take that capital M and break it up into its units, because in my head, I need it to unit. I cannot leave it as capital M. If you can in your head, go for it, but I just can't. I just can't. So you're always going to see me see capital M, break it up. Moles of Na2SO4 per liter times, does this look correct? No. This cannot be correct because those units will not cancel. So I would have to move this decimal place over 3 times or divide it by 1,000. That looks correct. So my liters will cancel. And double check my math. Not so bad, right? I'll have you do this problem. So I'm going to give you a few minutes. It does ask an additional question. So first, how many moles of sodium sulfate are in 125 milliliters of 0.125 molar aqueous sodium sulfate? Same exact setup as the problem before. So do the same method as before, but it asks for an additional step to go from moles to grams using the molecular weight. Now, we did figure out that sodium sulfate is Na2SO4. We need to figure out the molecular weight. So I'll give you a few moments to work on this problem, but make sure you answer both how many moles and then how many grams. So first, I found that the molecular weight of Na2SO4 was 142.037 grams per mole. Let's start with what we're given. If I need to figure out moles, I can multiply my molarity by volume, and that will give me moles. So in this problem, we can kind of break it up. So 0.125, that's moles of Na2SO4 per liter. And I need to multiply it by a liter. So 125 divided by 1,000, or move the decimal over 3 times, 0.125 liters. And the liters will cancel and give me 0.0156 moles of Na2SO4. So that is how we can figure out moles. The next step is to figure out grams. Okay. What am I going to put in a numerator here? Sorry, yes, that's in this numerator, but what about this numerator? No worries. Yes, so I will put 142.037 on top because I'm trying to convert moles to grams. So those moles will cancel. And I got 2.22 grams of Na2SO4. I do recommend double checking each question. If I was to ask you a short answer problem, make sure you read the question twice and ensure that you answer every part of it, because at least for myself, I kind of will kind of bypass a lot of the important questions and I'll miss easy points because I'm kind of flying through an exam stressed out about something else. So at least with our exams, you're not going to be really pressed for time, but I do recommend reading the question at least twice before you move on to the next one. And then if there is time before you turn an exam in, double check everything before you leave. Unless you're like are running out of time, that I understand. Are we good here? All right. So an alternative approach is using molarity as an equivalent. So we have done a lot of dimensional analysis since unit 1, where we create an equivalent and then we could set up the dimensional analysis equation. So molarity, of course, can be a conversion factor in dimensional analysis. If I'm looking for moles, you would just leave it as moles per liter, because if you're looking for moles, you want what you're looking for in the numerator and the given in the denominator when you're doing conversion. But if I'm looking for a volume, we can still use it as conversion factor, because if I flip it upside down, I now have liters in the numerator and moles in the denominator, so I can cancel anything out and be left with liters. Just note that if there is no number given, you can always assume it's a 1 in the denominator. So if I say I have 5 molar, that's 5 moles per 1 liter, or you can just do moles per liter. But yeah, you can always reverse it and put liters on top. It really just depends on what the question is asking for. So if a solution has a concentration of 0.5 molar, this means that 0.5 moles of solute are present in 1 liter of solution. So 0.5 moles equals 1 liter. So it's the same type of conversion factor we have set up in previous problems. So let's practice using that. How many grams of sodium chloride are typically found in a gallon, 3.79 liters of seawater, which is approximately 0.6 molar aqueous solution of sodium chloride? Hint: start with the volume and use the molarity as a conversion factor. So if I have 0.6 molar, that's 0.6 moles of NaCl over liters, or 0.6 moles equals 1 liter. So see how I wrote the liter on the denominator? You can also assume there's always a 1 out front. So it says, hint, start with the volume. So I'll start with 3.79 liters of NaCl, since we're focusing on NaCl. And it wants me to figure out how many, okay, so it's asking how many grams. Before I can get grams, what do I have to convert this to? So think about the periodic table elements. So the units on there are grams per mole. If I want to get to grams, what do I have to get to first? Moles. So if I set this up, I want moles, and then I can convert to grams. So that means I need to put 0.6 on top, because that's the numerator in moles. And I put the liters on the bottom, because I want those liters to cancel. And this is when you could break it up. You can equal this out and then move on. But if you want to put this all at once, if I go from moles to grams, I need the molecular weight of NaCl, which I think is 58.44 grams per mole. Yeah. Since there are 3 sig figs, let me fix this. 133. So with this setup, all my units cancel out, and I should be left with grams. And I'm going to keep reminding you, when you write this in your notes, when you do this on an exam, always include the units, because if you just left numbers, future you will not know what the hell is going on. And I'm speaking from experience, because future you will be very upset if you have no clue how to get a problem started, because current you is trying to skip that step. So always include those units, because you can catch a mistake. You can catch, if I was to put this as liters over grams, moles, there's no way this would make sense. So it has to be moles per liter. So do this for future you. Keep those units in there and make sure your units will convert. So example, using molarity as a conversion factor. In the lab, millimole needs 5 grams of sodium carbonate for a reaction, but our lab mate used the last of the solid sodium carbonate to make a 3 molar aqueous solution. How many milliliters of this solution does millimole need to provide 5 grams of sodium carbonate? So we're trying to like figure out how many milliliters are in this solution. So you want to use the molarity as a conversion. So even though I don't have a way to weigh out 5 grams, I'm just going to say, okay, I'm trying to use this 5 grams to base everything off of. So I'm going to write out 5 grams, sodium carbonate. I have Na plus. What is carbonate? CO. Yes, and then charge. Two minus. Definitely review this before the exam. Obviously, I'm not going to do a polyatomic like hardcore on it, but this is exactly how I can challenge you and hope that you remember your polyatomics, is I could write it out like that.
Didn't you say in Canvas, we have like a website? Right?
Yes, they're still there.
It's in the modules, right?
It's in their modules. I have a document you could print out with all of it.
Oh,
for
yeah,
you. Color coordinated, and I have practice polyatomics in the practice under homework.
Okay.
So I'm never gonna ask you to forget this because you will use this a lot. So this is how I can keep challenging your knowledge of polyatomics. So this one is a crisscross. So this would be Na2CO3. For me to be able to use molarity, I can't leave it like this because grams is not the same thing as moles per liter. I can't do conversion. So I always have to convert it into moles. So we need to figure out the molecular weight of Na2CO3. I already did it for you, so I will put that up here. That's the molecular weight of Na2CO3. But you can see if you didn't know how to create Na2CO3, this number will throw off everything else, and it sucks. Because if you did everything perfectly but just had this number wrong, it just sucks. I'm sorry, it just does. So I want my moles on top, and I want my grams on the bottom. It's asking us to go and figure out milliliters. I need to go from moles to liters. So this is when I need to incorporate my concentration. So concentration is moles per liter. But I want to get rid of moles. So to do that, I need to have liters in the numerator and moles in the denominator. So let me just prove that. That way those moles will cancel and I will be left with liters. All right. So if our concentration is 3, where will I put the 3? On the bottom, because the 3 belongs to the moles, not the liters. So you can put a 1 in front of the liters, or you can leave the liters as is. This problem is a little extra mean because it doesn't ask for liters. If you did all this hard work, you would be right, 100%. But the problem is asking for milliliters. So I'm just going to add an additional conversion in there just to make sure that our answer is in liters. Now, you could break this up and figure out liters and then convert at the very, very end, but just double check and make sure your units are correct because they were not very nice and they wanted it in milliliters. And just remember, this is just one example. You can do it all out at once if you're very comfortable with that. You could also break it up and go from grams to moles, enter, and then underneath it, you can go from grams to liters, enter, and then underneath that, you can go from liters to milliliters. So whatever works best for you, you're right either way. But yeah, this is a fun way of really challenging yourself. And I definitely recommend practicing these types of problems because if you can get this problem comfortably, you can do pretty much any of these problems. So you can maybe play around and change those numbers, and maybe instead of 5 grams, you can do 10 grams. Instead of 3 molar, you can do 6 molar. So I can ask you this question over and over again by just changing those numbers, but the math does not change. Okay. Any questions before we move on? Let's talk about what we deal with in the lab. That previous problem, we kind of set up a dilution because sometimes in lab, you can't just weigh things out. Example of this is HCl. If I want to make a 1 molar HCl solution, HCl is not a solid that I can go and weigh out and make this solution. It comes as a liquid. At room temperature, HCl is a liquid. So what we do is we have concentrated HCl, we take a little bit of that and we add it to a lot of water, create a desired concentration. That is called a dilution, where you have a stock, where stock tends to represent the more concentrated solution. You take a little bit of the concentrated solution, move it to a new volume vessel, and then you add water until you have your correct dilution. So this is a picture of that. So here you have the darker means more concentrated, right? There's more substance to it. They're removing a little bit, looks like they're removing 25 milliliters and adding it to a new volume vessel, just piece of glassware. And they are adding more water to it to create a more diluted version. So if you look at the difference in color here, I can tell the darker one's more concentrated and lighter one is less concentrated. And I could also do a calculation because sometimes you might be asked, what is the new concentration? So that's going to be these types of problems where you're going to be dealing with the dilution equation. Okay, so concentrated stock solutions, like an example of HCl and of subchemicals, are commonly found in labs. We can't always deal with stock, so we'll take the stock and create a new solution using a dilution equation. So when a chemist needs a solution of that chemical, they will dilute the stock solution to the concentration that they need. So dilution means adding more solvent or water to the concentrated solution to reduce its concentration. Since only solvent is added, the substance amount will remain constant. So that's why this equation works. So you have M1 represents concentration, and then M2 represents concentration, but the 1 tends to be your stock solution. Or the more concentrated one. So the bigger the concentration, that's your more concentrated. The 2 is your dilution or less concentrated. But I'll be honest, this equation works either way. If you said the 2s were the more concentrated, if you said the 1s were, it doesn't matter. You will get the right answer anyway, as long as you have them connected to each other the right way. I also want to point out that the units don't matter as long as you're consistent. So if I was to give you a volume in milliliters, you can use milliliters here as long as you have milliliters and milliliters. If you had liters and milliliters, it would not work out. But as long as you're consistent, you don't need to do additional work here, and I'll show you. Before we move on, in the derivation on the previous slide, the subscript 1 refers to the concentrated or stock solution, and the 2 refers to the diluted. But like I said, it doesn't matter as long as you're consistent. You'll be right either way if you were to flip-flop those numbers. This equation is derived from the equation that defines molarity. In the molarity equation, the volume of the solution must be in liters, but in this one, it doesn't matter. And then I do recommend using verse when you solve for these problems. Let's practice. So Bobcat is working on an experiment that requires very precise measurements of its solution concentration. His lab has a stock solution of copper sulfate with a concentration of 1.042 molar. For his experiment, he needs to prepare 25 milliliters of 0.3333 molar solution. How many milliliters of the stock solution does he need to dilute? So, verse. V is for variable. So as I read this, it says stock concentration is 1.042 molar. It's asking for how many milliliters of the stock do we need to make this new solution. So I do not know what V1 is. But I do know what our goal is. Our goal is to create a 0.3333 molar new solution. And that volume needs to be 25 milliliters. So that will be the hard part for this problem, is using verse to assign those variables. Just remember the 1s and the 2s need to be in the correct order. So 1s will be concentrated, 2s will be dilute. So that's why I was assigning M1 as 1.042 and V1 being what we're looking for. E is equation. So M1 V1 equals M2 V2. R is rearrange. So if we're trying to figure out what is V1, what could I do to this equation to rearrange it? I can divide by M1 on both sides. So V1 equals M2 V2 over M1. That's R for rearrange. S is going to be substitute and solve. The good news here is I don't need to do any substitution, meaning I don't have to convert this milliliters to liters. It just doesn't, it's not necessary. Because as long as I'm consistent, my answer will be correct. So solve. This is why it always works out. If my units are the same, they will cancel out when they're on top and bottom. So my answer will be in milliliters. And then plug this into your calculator to make sure you also got the same answer as me. And when I read the problem again, it does ask for milliliters, and that's why I did not waste my time converting it to liters. So whatever volume I'm looking for, I'm just going to have those units in there to save me some time. But I got practically 8 milliliters. So for me to make this new dilution, if I go back to the previous slide, I would need to take 8 milliliters of my stock 1.042 molar solution, move it to a piece of glassware that measured 25 milliliters, and then add enough liquid water to it until it hit 25 milliliters. So that's how this equation is being set up. How do you feel about that? I will always recommend verse for these because if you're comfortable with verse, it always works out. But once again, keep those units in there. Let's practice another one, and I'll let you do this. Millimole started with 25 milliliters of 0.4 molar copper sulfate solution. She added 25 milliliters of water to the solution. What is the concentration of the resulting solution? So I'll put the the equation up top. This is a little tricky, but I want you to try and solve for it. So let's go to V for variable. I'm just gonna assign these as the ones. So M1 will equal 0.4 molar. V1 equals 25 milliliters. Here's the trick. Is V2 25 milliliters? V2 is your total volume, and that's why this question is tricky. Because if you were to put 25 here, you would end up getting the same M2 if you put everything together. So V2 is your total. So 25 plus 25. So 50 milliliters. All right. So R for rearrange, we are looking for M2. So I have to divide by M2 on both sides. V2, sorry, yeah, sorry. V2. So M2 equals M1 V1 over V2. So last with the solve, so I'll put all the numbers in. And so M2 will equal, I think, 0.2. Sorry, like I can look at it and know it's 0.2 because it looks like it's 0.4 times a half. But I always type in my calculator just in case. Ooh, question. Copper sulfate. What is that? CuSO4. That is correct because copper is 2 plus and SO4 is 2 minus. So this one does not require a crisscross. So this is CuSO4. Job. Almost done. And then I don't think we're going to finish today. So we'll finish these slides on Friday. So I guess we'll do one more slide I'll discuss and then we'll end a couple minutes early. So just like on that previous one, if you combine two dilute aqueous solutions, you can usually add their volumes to find the total volume. V2 is always total volume. It's the bigger of the two volumes because it's usually the more dilute one. So sometimes you might be like given a little hint that says total volume is number. That's always your V2. Note that for concentrated solutions or for very precise analytical work, intermolecular forces can result in a volume concentration or expansion. But y'all don't have to worry about this in Gen Chem 1 or even engineering. But this is something we think about when we think of higher chem. So if no other information is provided, assume that the total volume is the sum of these volumes. But typically they'll use, I want it to be this volume or the total volume is this. Any questions? All right. So we will start on slide 26 when we come back on Friday. I will open up quiz 8 and your homework for this. So please, 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 at least before Friday or this weekend hits, get your other stuff done. So the weekend hits, you can focus on study. You get your homeworks out the way, get your quizzes out the way.
What's your last homework?
The one that I opened today will be the last.
Okay.
Yes, I don't want to give you the maximum amount of time, and I feel like Friday's not enough time. So today will be open, but please, please, please get what you can done. And then obviously email me, or come chat with me if you have any questions.
You're just right above the.
I'm right above here by the stock room. So if you know where the stock room is, so it's just right there, Chem 215.